What's going on, Sarah? 10:30 or so here in Jerusalem, Israel. Thursday night. It's Thursday during the day where you are, probably like noon or something like that. Or maybe it's, yeah, I think it's about that right now. So what I'm going to do is give you a very, very quick overview of the first part of your 37 WhatsApp pics about chemistry. My goodness, it's quite a bit, but make it easy, make it fun. I know the shades don't really have anything to do with it, but this way you don't see how tired I am right now. So, I hope you're feeling better, first of all. And here we go. Got my little travel whiteboard with me. And upon it, here's what I drew. One of these things I'm sure you've seen and dealt with, and it's a phase diagram. And by the way, if you are already comfortable with this, this may not be as helpful. Maybe it'll just reinforce what you already are comfortable with, which is good. And if you are not comfortable with it, hopefully you will be more comfortable with it after I stop yapping. Okay, so what one of these things is in a nutshell is it says how some substances, temperature changes over time. Temperature, therefore, is on the vertical axis always, and time is always on the horizontal axis. And check it out. We got the temperature rising, the temperature ain't rising. The temperature's rising, the temperature ain't rising, and then the temperature's rising again. And I just realized right now I forgot your pink marker, but next video I'll hook you up, okay? All right, so looks like a funny little staircase type deal. We have phase changes on any horizontal part, okay? If heat is being pumped into something, whether it's a block of ice, a block of some metal, wood, I don't know, anything at all, and its temperature is not changing, but heat's still coming into it, it has to be doing something. So what's happening if the temperature of the item is not rising with time, like going up to the right, basically? If it's just staying flat, that means the heat's doing something else other than increasing its temperature. And what that thing is breaking intermolecular bonds. Not within the same molecule, but molecule of ice, another molecule of ice. They're bonded. Those little bonds are going to be broken with that heat energy. So ice is going to be transformed into liquid water. So usually if your phase diagram has two little plateaus, we call them, phase diagram. The first one, where the temperature is lower, it's going to be melting. And the second one is going to be evaporating, which means this has to be solid, this has to be liquid, and that has to be gas. Okay? If something starts as a solid and heat's pumped into it, its temperature is going to rise until it reaches its melting point, at which it will begin to not rise again in temperature, but it's going to start to melt. Then once every single intermolecular bond is broken, like every single, like pretend you're holding hands, like there's 100 people holding hands, right? Those would be like the intermolecular bonds. So let's say that everybody lets go of everybody else's hand. So now all the molecules are disengaged from each other. They can flow around, they can move around and stuff like that. So now it's a liquid, okay? Now we're here. And as heat energy is being pumped into that system, temperature is rising, 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 but eventually it's going to get way too hot and it's not going to be a liquid anymore. It's going to now, because remember in a liquid, you know, they're still attached, let's say. It's still like a puddle, okay? It's still a group of liquid that's not flying out into the atmosphere like a gas would, but it's getting there because when we add more heat energy into a liquid, and its temperature doesn't rise anymore, that means it is being heated to the point where more bonds are being broken, the liquid bonds are being broken, and now that substance is a gas. And any amount of heat energy beyond that is just going to superheat that vapor going forward. Okay? So if this was too long-winded and you already knew it, okay, big deal. Congratulations. Maybe, hopefully this helped you, like I said earlier, get reinforced with it, okay? But if not, go ahead and watch this a couple of times and see if it makes sense, okay? Or if you're in between, hopefully this helps as well. So now this is the visual explanation of a phase diagram. Basically, in a nutshell, the longer time goes on, the more heat is pumped in, and the substance, whatever we're talking about, is going to turn from a solid to a liquid to a gas, and in between it's going to melt first to go from a solid to a liquid, then it's going to evaporate to go from a liquid to a gas. By the way, if we were to completely, that's not going to work, flip this whiteboard around and have it be translucent, if this is going to go completely mirror image in the opposite way, that means heat's being removed. And instead of evaporating, stuff is condensing, and instead of melting, stuff is freezing. Sometimes teachers try to do that with you. They'll teach it this way, and then they'll say, oh, actually we're not heating stuff up, we're cooling stuff down. So that's the idea. Now, this is the background of the situation. Okay, you text me if you have any questions upon that. But what I want to do right now is, because your chemistry class is not all theory, of course, it's got some numbers going on. So I'm going to give you a typical example that could be useful to you. Okay? So the basic idea of this example is you want to find out how much heat is pumped into something. And what they'll do is they'll tell you, hey, a certain mass of a certain substance starts out as a liquid or starts out as a solid, okay? And then you want to know what happens when it goes from this temperature to this temperature, okay? And there's a very simple formula that goes along with it. If you've heard it, it's Q equals MCAT or Q equals SMAT or Q SMAT. Let me show you what I mean. This is the first one I said. It's called Q equals MCAT. Okay, that's not a real A. It's the Greek letter delta, which means change in. So really, it's the amount of heat, lowercase q, equals the mass of the substance you're given in grams, or whatever units the C is, okay? C is specific heat capacity, okay? And AT is really like delta T, which means change in temperature. So really what this is saying is the amount of heat that goes into something, you can barely even see that Q, I'm going to rewrite it. Okay. So the amount of heat that goes into a substance equals its mass times its specific heat capacity times its change in temperature. Now you might be asking, what is the specific heat capacity? What it is it's this property of a substance, okay? It's the amount of energy required, then usually energy is in joules or sometimes kilojoules, that will raise any amount of a substance by 1 degree Celsius or Kelvin. So because there are alternate units for energy, sometimes mass, sometimes temperature, you could get joules per gram Celsius, you could get kilojoules per mole Kelvin, but it's still the same stuff. It's like energy per divided by mass times temperature. So it's something like this. So here's basically what we got in some form, in some units. That C can be written sometimes as CS, like capacity of specific heat. And it is either joules or kilojoules, grams or moles, Celsius or Kelvin. But really it's some kind of energy divided by some kind of mass times some kind of temperature. Okay? So for instance, water, the most common substance there is, has liquid water, by the way, has a specific heat capacity of this. Okay, liquid water specific heat capacity is 4.184 joules per gram Celsius. That's how that's read. It's kind of like G hyphen Celsius, like grams hyphen Celsius. It's hyphenated in the denominator there. And what it means is it takes 4.184 joules of heat energy to raise 1 gram of liquid water by 1 degree Celsius. Great. Okay, that's how much it is. There's a whole table of values, I think, in your notes, or if not in your notes, in your textbook that will tell you that. Okay, that's usually given to you. The only time it's not given to you is if you're given everything else, you got to solve for it using that formula. By the way, another way that formula could be written is something like this. Q equals SMAT, or SM delta T, which is read QSMAT, not Q equals MCAT, but it's the same idea. Instead of specific heat being C for heat capacity, they call S specific heat. And then the M is the same as this M, it's mass, and then delta T is the same as delta T. I don't know which one you use, but they're the same darn thing. Cool? So, let's check out a typical problem in a typical scenario. I don't want to make this video too long, but there's like an easy, medium, and a hard level for this stuff, so I'm going to make numbers up. Okay, you'll be given actual numbers in the interest of time in this video. I don't want to make it too long, so I'll just make up my own numbers, okay? But I will use water just for this. All right, well, let's say you have 20 grams of water, okay? Oh, what does it say? How much heat is needed to raise the temperature of the water from 15 degrees to 25 degrees Celsius? So it starts at 15 degrees, goes to 25 degrees. They're not going to tell you what phase of matter that's in. They're not going to tell you if that's a solid, a liquid, or a gas, but it's up to you to know that if the boiling point is at 100 of liquid water and the melting / freezing point of water is at 0, hey, these guys are between 0 and 100, so it's got to be going from liquid state to the liquid state, just going up 10 degrees. So that's the bare bones easiest form of this type of problem. All you do, I'm going to use Q equals MCAT. If you use Q equals M, or Q SMAT, if you use S instead of C for specific heat, it's the same thing. Okay, so I'm going to say Q equals MCAT, like that. We're asked for the heat, so that's my unknown. I'm going to keep it as an unknown. The mass is 20 grams. The specific heat we just talked about is 4.184 joules per gram Celsius. And the change in temperature, it's always the end minus the beginning, so it goes from 15 to 25. It ends at 25. It starts at 15, so 25 minus 15, I taught you well, I hope, enough in math, is 10. And then what you end up with is you have 20 times 10. Notice you have grams, you have Celsius. Those cancel out down there because those are in the denominator. These are regular in the numerator, so those will cancel. The only units left will be J for joules. Heat is in joules. That's what we want. So whatever the heck this times that is. So 200 times that. So it's basically going to be 418, 836.8 roughly. All right. So 836.8 joules of heat is basically what we're dealing with to raise water 10 degrees, actually 20 grams of water, 10 degrees Celsius. Sound good? Now, if that made sense, if you're already cool with that, then you just like looking at my goofy sunglasses. Awesome. I hope this was relatively entertaining. Now, if you need something more than that, I'm going to show you what's up. Because maybe, just maybe you have to go over a phase change. So let's see what's up with that. And again, I'm going to make up my values. I should know the values for water. I don't. It's late. I'm still jet lagged. I've been here, not here in Jerusalem, but I've been out of the country for like a week and a half, almost 2 weeks. I should be used to the time change. I'm not yet. Forgive me. So let's say same exact problem, but now I want to go from -5 degrees Celsius to 25 degrees Celsius. And you realize, oh shit, 0 degrees, which is in between -5 and 25. 0 degrees is the melting point. I got to do something special there. Okay. So this ends up being a 3-step process. Okay. And it's like you've got to go chronologically, got to go in order. Okay. So we're going to go from where it starts. First, it's got to go up to the melting point. So it's got to go from -5 to 0. So it's going to be a regular one of these. Q equals MCAT. So the amount of heat required is going to be the 20 grams. It's going to be, now solid water, ice, has a different specific heat capacity. Okay. I forget what it is. I'm going to make it up off the top of my head. I'm just going to say it's 8.414 just to use the same digits. And then from -5 to 0 degrees is only 5 degrees. Okay. So I'm going to put a 5 right here. So all I'm doing is I'm taking it from its -5 up to the threshold of where it's going to start to melt. Okay. And then 20 times 5 is 100. That's why I chose those numbers. And if I multiply this number by 100, I get 841.4 joules. That's for step 1. Now, step 3 I'm going to do before step 2 because it's the exact same formula as this, but it's going to go now from 0 to 25. Okay? So step 3 is the exact same. I'm going to write it down here at the bottom. Step 3 is going to be another Q equals MCAT, so Q equals the 20 grams. But now, after we're going from 0 to 25, we're already in the liquid phase. So we revert back to the water's liquid specific heat, which is 4.184. So that goes here. And finally, we got to say how far or how many degrees does it go up from 0 to 25? I think that's 25. So I'm going to put it right there. So 20 times 25 is 500. 500 times that is going to be roughly 2100. I'm just going to, because I'm tired, I know you can do the math. So I'm going to say like 2100 joules. So these two processes, we've went from 5 to 0. And then separately, we've gone from 0 to 25 because we encounter a phase change. If there was no phase change bridge we crossed over, we could just do one step and call it a day. Those are the nicest kind. Those are the kind I did first. But because we go through a phase change, in this case, solid to liquid. So really, we're doing this path. This was step 1. This was step 3, right? Step 1 was going from -5 to 0. Step 3 is going from 0 to 25. But now, the temperature doesn't change. The phase changes from solid to liquid. So, step 2 is going to be a different formula. But it's a very simple formula. It's a very simple formula. Okay? What it is this. You have these two quantities. Okay? You have the heat of fusion and you have the heat of vaporization. Okay? The heat of fusion sounds like when stuff fuses together. In other words, like when water becomes ice. But it's also the same as when ice becomes water. It goes both ways. So the heat of fusion is for both melting and for freezing. In this case, we're going to do melting. So let's just say, I forget, your textbook, your notes have the values. So let's say the heat of fusion of water and by the way, here's the basic formula for it. The heat of fusion, it's an amount of heat per grams or per moles. So it's Q, heat, divided by M, mass. And you'll be told whether you have moles or whether you have grams, okay? But just for now, let's say that's the thing. But I want to solve for heat. If I want to solve for the Q, which is the heat value, I multiply both sides by M, okay? And I'd end up with this. Basically, Q equals the heat of fusion times the mass. So let's say the heat of fusion was, I don't know, 20 kilojoules. Let's just say 20 kilojoules, okay, of water. 20 kilojoules of heat for every gram of water, okay? Or 2,000. Let's just do 2,000. So 2,000 joules, and we do have 20 grams of water. That equals 40,000 joules right there. Okay? So in plain English, what this says is, it's going to take us 840 or so joules of heat to raise from -5 to 0. Then to break all those solid water ice bonds to get the water liquid form, we're going to need an additional 40,000 joules of heat. Okay? That comes from this formula, where the capital H is the heat, not the capacity, it's the heat of fusion. Okay? And you'll be given that. That is always provided for you. So in that case, it's like a plug and chug. And finally, step 3 was going from 0 degrees to 25 degrees. And that we used Q equals MCAT again, so we just find that. So basically, the last thing you got to do is you got to add them all up. Everything's circled. So 841.4 plus 40,000 plus 21,000, or sorry, 2,100 joules. And we get something like 43,000 roughly. It's like 42.9 or something like that. So either 42,900 joules of heat energy is required to take ice from -5 to 0 through the liquid phase, through the solid phase to the liquid phase, and then up to 25 degrees Celsius. Nearly 43 kilojoules, or 42,900 or so regular joules of heat. That's how a problem like this goes. If, God forbid, they ask you from like -5 to like 125, guess what? There's going to be step 4 and step 5. Step 1 would be -5 to 0, using Q equals MCAT. Step 2 would be the heat of fusion formula, which is the same as the heat of melting formula, okay? Which was this right here, Q equals HM. And you'd be given the heat of fusion. Step 3, got to go from 0 to 100. That's Q equals MCAT. Step 4, I now got to go from the liquid to the gas phase, because above 100 degrees, it's going to be vapor, which is a gas. So I got to do another one of these guys, but instead of the heat of fusion, because it's going from liquid to gas, I'd have to use the heat of vaporization value, which would also be given to you. So it's just a straight up plug and chug, and you use the same mass of water or ice that you originally were dealing with. And then finally, step 5 would be Q equals MCAT from 100 degrees to 125 degrees. There we have it. So hopefully you found this helpful. Hopefully this wasn't too long and tedious and boring. And hopefully you already knew some of this stuff. So this is just going to be like a little solidifier of the technique and the basics for you. Or if you really didn't know a whole lot about it, you were just looking at your notes saying like, what the hell is this stuff? Hopefully this gives you a good foothold, a good firm like base of understanding for what's up. Either way, text me with what your thoughts are, with any questions you have. And honestly, the most important thing is feel better. And we'll talk soon. Let me know how this was.